this class, we will start to talk about disaccharides. Disaccharides formed by two monosaccharide units covalently bonded to each other. So those two monosaccharides will condense together, eliminating one water molecule to form a disaccharide. So one of the monosaccharide units will serve as the heavy acetal, and the other one will serve as an alcohol to form an acetal linkage. And we call this linkage glycosidic linkage. Okay, so glycosidic linkage is used in carbohydrate chemistry to refer to the bond that link two monosaccharides unit together. The first disaccharide we will look at is called maltose. Maltose is formed by two glucopyranose units linked together through a glycosidic bond between carbon 1 of one unit and carbon 4 of the other unit. And the carbon 1 of the first unit will be in the alpha form. So let's take a look at the structure. Okay, the first unit, carbon 1 is in the alpha form, so the O on carbon 1 is pointing down, and it forms an acetal linkage with the OH on carbon 4 of the second unit. Okay, so here it is. We call it an alpha 1,4 linkage. So we use this notation: alpha parenthesis 1 an arrow to 4. Okay, so alpha 1,4 linkage. This is a glycosidic linkage. The 6-membered ring sugars will be put in the chair conformation. So let's see the chair conformation for maltose. All right, so in the first unit, carbon 1 has an alpha oxygen, which means the O is pointing down on the axial position. And the carbon 4 OH is on equatorial, so they form a linkage here, alpha 1,4 linkage. All right. The second disaccharide we will look at is called isomaltose. It's formed by two glucopyranose units in the alpha form, but it's alpha 1,6 instead of 1,4. So this is the structure in the chair conformation. The first unit is the same as the one in maltose. It's an alpha glucopyranose, and it forms a linkage with carbon 6 of the second unit. Okay, the CH2OH part of the second unit. So this is the alpha 1,6 linkage. The third disaccharide we will look at is cellulose. It's formed by two glucopyranose units, but in the beta form, it has a beta 1,4 linkage. So the first units will be in the beta form, which means on carbon 1, the O will be pointing up. And it's going to make a link to carbon 4 of the second unit. Okay, so this is the beta 1,4 glycosidic linkage. And here is the structure in the chair conformation. Carbon 1, a link to carbon 4 in the beta 4. Alright. So the maltose and the cellobials, they are diastereomers. The only difference is the absolute configuration on the carbon 1 of the first unit, right? One is down, the other is up. Okay, one is alpha, the other is beta. They are diastereomers, but they differ significantly in the three-dimensional shape in space. So they have different properties, and one enzyme that can hydrolyze the alpha 1,4 linkage cannot do the beta 1,4 linkage. Okay, we will revisit this concept later. So maltase is the enzyme that can hydrolyze the cleavage of alpha 1,4 linkage. Okay, ASE ending, that's the enzyme. On the other hand, emulsin is an enzyme that can hydrolyze beta 1,4 linkage. Okay, these two enzymes are very specific. They can work on only one type of linkage, not the other. Next, disaccharides, lactose. Lactose is one of the major components in the milk. Lactose is formed by one D-glucopyranose unit and one D-galactopyranose unit. And the galactose is the one that forms the glycosidic bond. The bond is in the beta 1,4,4. So let's see the structure. The first unit is galactose. Second unit, glucose. So first unit, carbon 4 has a different configuration as glucose. Remember, galactose is a C4 aptamer to glucose. And the first unit, galactose, is in the beta form. So carbon 1, the oxygen will be pointing up, and it's forming a linkage to carbon 4 of the second unit, which is glucose. So on carbon 4 of the second unit, this O is pointing down. So this is a beta 1,4 glycosidic linkage. That's the lactose. In chair conformation, this is what we have. The first unit, carbon 4, has an axial OH for galactose. Alright, so the beta 1,4 linkage. So for the first 4 disaccharides that we have talked about so far, the linkage alpha 1,4, beta 1,4, or alpha 1,6, these are all head-to-tail linkage, meaning it's one anomeric carbon reacting with another OH that is not anomeric. So if you consider anomeric carbon as the head, and a non-anomeric carbon will be the tail. The last disaccharide we will look at is sucrose, which is the table sugar. It's formed by one D-glucopyranose unit in the alpha form and one D-fructofuranose unit in the beta form. The linkage is called alpha-beta 1,2 linkage. So lots of information are provided here. All right. So glucose is in the 6-membered ring, pyranose, and the fructose is in the 5-membered ring. It's a furanose. And the carbon 1 of glucose is the anomeric carbon. Carbon 2 of fructose is the anomeric carbon. So in sucrose, the 2 anomeric carbons are linked together. And this is the head-to-head linkage, unlike the ones we have just talked about. So there will be no free anomeric carbons. No free anomeric OH groups. There will be only one form, no open chain. So all the anomeric carbons in this disaccharide will be locked. Let's take a look at the structure. Okay, so glucose unit in the alpha form, carbon 1 has an O pointing down. Fructose unit in the beta form, carbon 2, the anomeric carbon is carbon 2, has the O pointing up. So this linkage is called alpha-beta 1,2 linkage. It's a head-to-head linkage. And the sucrose is a non-reducing sugar because it does not have a free OH on the anomeric carbon. In all the previous cases, the disaccharides, one anomeric carbon unit is used to make the glycosidic linkage, but the second unit will have a free OH on anomeric carbon. So the second unit is still in the hemiacetal form that the ring can open to give the aldehyde functional group, which can serve as a reducing agent. But in sucrose, no, we don't have that free OH on anomeric carbon. So sucrose is the only non-reducing sugar that we know as a disaccharide. Another thing that's very interesting about sucrose is that it's an invert sugar. When sucrose is hydrolyzed under acidic condition, it will give 1 unit of glucose and 1 unit of fructose. Here is the optical rotation of these 3 compounds. Sucrose, positive 66 degrees. Glucose, positive 52 degrees. And fructose, negative 92 degrees. Remember, we talked about this. D-glucose is dextrose, which means the rotation is positive. And the D-fructose is levulose, which means the optical rotation is negative. And the number for fructose, the rotation absolute number is bigger than that for glucose. So overall, when we get 2 units of these 2 sugars, the overall optical rotation, the net is negative 40 degrees. So sucrose itself has a positive rotation. After it's hydrolyzed, the hydrolyzed mixture will have a negative rotation. So the optical rotation is inverted when sucrose is hydrolyzed. That's why we call it an invert sugar.